Okay, today we're going to look at absolute versus conditional convergence and what those two things mean. And we're talking most of the time when we talk about absolute versus conditional convergence is we talk about or we're working with alternating series. Because remember, alternating series has that alternating piece where they go from positive one to where they alternate between positive and sign, negative and sign, positive and sign, or vice versa. So before we get there, let's look at two series that are very similar, yet are really quite different. So if we look at the first one of the harmonic series, remember this one's called the harmonic series. If we write out the first 5 terms, then we're going to start with n equals 1. So it would be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So that would be the first 5 terms. Now, if we talk about whether or not it converges or diverges, it's a p-series where p is equal to 1, which is, less than or equal to 1. So therefore, it diverges by p-series test. Okay? Now, if we add to that a piece that is negative 1 to the n, if we write out the first 5 terms of that, if I plug in 1 for my first term, it would be negative 1 over 1. If I plug in 2, it would be a positive 1 over 2. If I plug in 3, it would be a negative 1 over 3, then a positive 1 over 4, then a negative 1 over 5, and then so on and so forth. So it is almost the same, except for now we're alternating in sign. Well, because we have that negative 1 to the n, we can now use the alternating series test to determine if it converges. And the alternating series test, guys, is not as strict as the other tests, okay? The subtracting off does things to the sum that helps it converge. So we would first need to identify a sub n, which is just going to be 1 over n, because remember we ignore the negative 1 to the n part. And so it's got 2 conditions. The first one is the limit as n goes to infinity of 1 over n. It is 0, so the first condition is met. Then our second condition, remember, is that it's decreasing. So 1 over n plus 1 is less than 1 over n. So that condition is met. So therefore, this one converges by alternating series test. Okay, so we've got 2 series that look very much the same, but but to get it to converge, it requires the alternating piece. Okay, so that leads us into absolute versus conditional convergence. Basically, we're trying to decide, does it require the alternating piece in order to converge? So for this guy, we would say it has conditional convergence because it converges conditionally upon having the negative 1 to the n. Without it, it diverges. Now, absolute is just like absolute value. If we get rid of the alternating piece, okay, or we take the absolute value of all of the terms and we make them all positive, does it still converge? Well, in this case, it didn't. It diverged without the alternating piece. So that's what we're looking at. So a series is said to have absolute convergence if the absolute value of the series converges. Okay, so we have absolute convergence if the absolute value of the series converges. That's what this guy is. These are the absolute value bars. If it has absolute convergence, then then you can remove the absolute values and it will converge as well. Okay, so putting the absolute value bars around it is more strict, I guess, let's say, than not having the absolute values. If it has conditional convergence, then without the absolute value bars, it will converge, but with the absolute value bars, it will diverge. So we saw that on these 2 series here. We would say that negative 1 to the n over n has conditional convergence because when we took the absolute value of the terms, then it diverged. But when we put the alternating piece back in and we left it the way it was, then it converged, okay? This is not as hard as it's sounding. So let's see what we're going to do. Okay, so on our first thing, we've got -1 to the n plus 1 over the square root of n. We always check for absolute convergence first, because if we can get absolute convergence, then we're done and we don't have to try anything else, okay? So absolute convergence means I'm going to take the absolute value of this, and so basically it means what I'm working with is 1 over the square root of n. Okay, I'm ignoring the -1 to the n piece. Now, I can use any test but the alternating series test to try and determine if it converges. Well, this is a p-series, so this is like 1 over n to the 1/2. So our p-value is 1/2, which is less than or equal to 1, so therefore we diverge. So that means it does not have absolute convergence, okay? We couldn't get it to converge without the alternating piece. Okay, so now we're going to check for conditional. We're going to go put the alternating piece back in, and we're going to use the alternating series test. So our a sub n is still our same guy, 1 over the square root of n, but we have two different conditions to check. So our first condition is that the limit as n goes to infinity of 1 over the square root of n is equal to 0. Well, that is true. It's bottom heavy. So that condition is met. The second condition is that it's decreasing. So is 1 over the square root of n plus 1 less than 1 over the square root of n? Well, yes, it is. So that means we converged with the alternating piece. So our conclusion is that we have conditional convergence. And that's ultimately what we're asking for. Okay, let's look at the next guy. We have -1 to the n plus 1 over the square root of n cubed. So without the alternating piece, it would be 1 over the square root of n cubed, which would be 1 over n to the 3/2. It's another p-series. So our p is equal to 3/2 this time, which is greater than 1, so therefore it converges. Well, if this guy converges, then we automatically know this guy is going to converge, and we say it has absolute convergence. Okay? That's why we start with this one, because if we get this one to converge, then we can basically just write our answer. All right, next one, cosine of pi n over n squared. Now, we've looked at this problem before, and remember, we've said that that cosine of pi n is our -1 to the n. So without the alternating piece, it would be 1 over n squared. So p would be 2, which would be greater than 1. So therefore, this guy converges by p-series. That means this guy automatically converges, and we have absolute convergence. We converged with the absolute value of the terms. All right, this guy, if we remove the -1 to the n, then our equation is n over n plus 1. So we need to decide if that converges or diverges. Well, if I look at this test, I'm thinking to myself, well, that's an equal. So we would have the limit as n goes to infinity of n over n plus 1 is equal to 1, which is not 0. So this guy is going to diverge. Now, when we come over here, this guy is going to fail the alternating series test as well, because if we're looking at n over n plus 1, the first condition is going to be the limit as n goes to infinity of n over n plus 1, and we need that to equal 0, which it does not. So that means it failed both, so we say it diverges. So if it fails both of these, then it's a divergent series. Okay, now we have this guy. So if we ignore the -1 to the n, we have 1 over n minus 1. Okay, so how are we going to prove that convergent? Well, that is going to be close to a p-series. So I am going to compare it to b sub n, which is 1 over n, where p is equal to 1, which is less than or equal to 1, so therefore it diverges. So I'm going to try 1 over n minus 1 and 1 over n. So what happens when I take one away from the denominator? Well, the fraction gets bigger, so now I'm more than a divergent, so this guy diverges, okay? Now, over here, I'm going to try my alternating series test. So we have 1 over n minus 1. So my first condition is the limit as n goes to infinity of 1 over n minus 1 is equal to 0. That is, it's bottom heavy. My second condition is decreasing, so 1 over n plus 1 minus 1 needs to be less than 1 over n minus 1. Well, 1 over n is less than 1 over n minus 1 because remember n minus 1 is making your denominator bigger. So that condition is met. So therefore it has conditional convergence. Okay, it needs the alternating piece to converge. The convergence is conditional upon the alternating piece. All right, last one, we have negative 1 to the n over n plus 1 quantity squared. So if we did our a sub n as 1 over n plus 1 quantity squared, I think what I'm going to do is, let's see, I'm going to compare that. So b sub n is going to be the sum of 1 over n squared, okay? Because if I think about foiling that out. So 1 over n squared, that means p is equal to 2, which is greater than 1, so therefore it converges. So now I'm going to look at 1 over n plus 1 squared compared to 1 over n squared. Well, adding 1 to the bottom of the denominator makes it smaller, so I am less than a convergent. So that means this guy converges. So if that converges, then so does this, so we have absolute convergence. Okay? All right, so now, when do we use this? The only time we use this is when the directions say determine if the series converges absolutely, conditionally, or diverges. So it has to use the words converge absolutely or converge conditionally before you can use that test, okay? All right, so that is it for convergence and divergence. We'll move on to something a little bit different next lesson, and we're going to look for what are called intervals of convergence and radius of convergence next time. So if you have any questions, guys, come see me. Thanks. Bye.